Hey there, Math Hoppers! In this video lesson, we will learn how to graph the sine and cosine functions, and we'll learn what in the world a sinusoidal function is. So this is the parent function for sine. It's y equals sine x, sometimes y equals sine theta, the variable changes. But we have seen this when we learned the sine values for 0, 30, 45, and 90 degrees. What we're going to do today is learn the properties of it and learn how to graph it and its transformations. So let's start with the domain. What is the set of all allowed inputs for this graph? And if you look along the horizontal axis, you will see radian values. And there are no inputs or radian values that do not return a sine value. Therefore, the domain of the sine function is all real numbers or negative infinity to infinity. What is the range? Clearly, the range is not going to be negative infinity to infinity. We can see that the output, the highest output we can see here is 1. And the lowest is negative 1. So the range for the parent sine function is negative 1 to 1. Let's talk about continuity. Is the graph of y equals sine of x continuous? Can I trace it without having to pick up my pencil? And we did talk about how there were no breaks in the graph, meaning yes, it is continuous. Now let's talk about whether it's increasing or decreasing. We can see that there are many intervals where it is both increasing and decreasing, but we're not going to go ahead and list those simply because sine and cosine, for that matter, are functions that are alternately increasing and decreasing periodically. All right, let's talk about symmetry. Remember, symmetry doesn't have to mean vertical symmetry with the y-axis. You also have symmetric with the origin, point symmetry, right? Those odd functions we learned had symmetry with the origin. And that's exactly what the graph of y equals sine of x has. If you look right here at the origin, point symmetry means you have the point xy, and you have the counterpoint for it, negative x, negative y. So this graph is symmetric with the origin, making it an odd function. Not odd meaning weird, but odd meaning odd, even, and neither. This is an odd function. Okay, is it bounded or unbounded? Well, we can see that it's bounded above here at 1, and it's bounded below at negative 1. So we call this a bounded function. It doesn't go off to infinity anywhere. How about an absolute maximum? Well, we just said it was bounded above. Where was it bounded above? Maximum happens at 1. What about the minimum? The minimum is negative 1. Are there any asymptotes for this graph? I hope not. We already said it was continuous. So there are no asymptotes for this graph. Now let's talk about the end behavior. Remember, the end behavior describes what a function is doing, or the intended height of a function, what it's approaching as x approaches both positive and negative infinity. It's also known as the limit of a function. And for sine, the limit as x approaches either positive or negative infinity does not exist because the function oscillates between 1 and negative 1. So it doesn't go off and approach some value that it never reaches. It oscillates between negative 1 and 1 throughout the wave. So let's use the unit circle to graph sine. Remember, we learned all of the values of sine from the unit circle. Well, we used it and then we plotted them on the unit circle. But we used circles to figure out what our sine values were. We had a circle, we built a right triangle. We're going to use that same circle to graph this sine wave. What we have to remember is that the points x, y along the circle are really cosine sine values. Sine is your y coordinate and cosine is your x coordinate. So the sine of any angle or any input is going to be the y coordinate. So let's put a partial unit circle up. And I'm putting a partial one because these are the 5 points we're going to use when we graph our sine and cosine graphs. We're going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. And let's put a more detailed sine graph up, and let's look at the relationship here. So I said that the sine values are your y coordinates. Therefore, we should be able to look at the unit circle, like right here at 0 radians or 0 degrees, and we see that at 0 we have the point 1, 0. The y coordinate is 0, therefore the sine value for 0 radians is 0. Moving along the circle, if we go up to pi over 2, we have the point 0, 1. The y coordinate is 1. The sine value for pi over 2, or 90 degrees, is 1. Moving along, the circle, we go down to pi. Pi has the point -1, 0. Again, the y-coordinate is 0. So the sine value for pi is 0. Moving along to 3 pi over 2, we have the point 0, -1. The y-coordinate is -1. Therefore, for 3 pi over 2, the sine value is -1. And ending where we started, 0 and 2 pi have the same exact point. 2 pi is the point 1, 0. The y-coordinate is 0. Therefore, sine ends at 0. So this is one complete cycle of sine. We go from 0 to 1 to 0 to -1 back to 0. This is one complete cycle of sine. Right here, this little purple that I'm tracing right here is one complete sine wave. So you'll notice that we keep getting the same values returned to us over and over. 0, 1, 0, -1, 0. The same values will be returned to us because sine is periodic. When a function is periodic, it means it returns the same outputs over and over at regular intervals. So what becomes very important is what is the period of the sine function. The period is just how long it takes to complete one cycle of that function. So we can see here, we used the unit circle to graph this. We went all around the unit circle, starting at 0 and ending at 2 pi. Therefore, from the unit circle, we can see that the period of sine is 2 pi radians, or 360 degrees, meaning it takes sine 2 pi radians to make a complete cycle. All right, let's do the same with cosine. So the cosine graph is again a wave, and we are looking at this at different points along the wave. You'll notice that the cosine graph starts up at 1 rather than 0 like the sine graph. So this is the parent function, y equals cosine of x, sometimes y equals cosine of theta. And let's look at all of the properties, starting with the domain. So as we look along the horizontal axis, there are no values or inputs that do not return a cosine value. So the domain, again, is all real values, -infinity to infinity. Our range should look pretty familiar. The highest point we reach is 1. The lowest output we reach is -1. Our range goes from -1 to 1 inclusive. Talking about continuity, the graph of cosine is a wave, just like sine, and it is continuous. I can trace it without picking up my pencil. For the intervals where it's increasing and decreasing, or increasing or decreasing, again, we see there are many intervals where it's both increasing and then decreasing. That is because the graph of cosine alternately increases and decreases periodically, so we will not state all of those intervals. Is this graph symmetric? Now, it doesn't have point symmetry, but if you look at this, if we were to fold this graph over on this vertical axis here, it would match up. It is symmetric with the y-axis, making it an even function. If you remember back to algebra when we learned even and odd functions. So again, it's not an odd function. It doesn't have point symmetry with the origin, but it is symmetric with the y-axis. It can fold over on itself, making it an even function. Is it bounded or unbounded? Well, it does not go off to infinity anywhere. It is pretty clearly bounded, just like our sine function was, bounded above and bounded below. The absolute maximum is 1. The absolute minimum is -1. There are no asymptotes, just like there were none in the sine function. And if we talk about the end behavior, or the limit as x approaches positive and negative infinity, just like sine, the limit of cosine does not exist because it oscillates between 1 and -1. Can we use the unit circle to graph cosine just like sine? Absolutely, because if you remember, those points along the circle, those xy coordinates are cosine sine points, right, or cosine sine values. So the x coordinate is the value of cosine. So if we look at our partial unit circle here, for 0 all the way to 2 pi, every x coordinate is going to be your cosine value. Now, if you don't remember why this is, go back and watch the sine and cosine values of any angle. Let's look at a more detailed graph of the cosine function with the points labeled. And let's go around the circle. Starting at 0 degrees or 0 radians, we have the point 1, 0. The x-coordinate is 1. Therefore, the cosine value at 0 radians is 1. The graph starts up at 1 here. Going around, pi over 2 or 90 degrees is the point 0, 1. The x-coordinate is 0. Therefore, cosine is 0. Moving around the circle, going to pi. Pi has the point -1, 0. -1 is the x-coordinate, so the cosine value is -1. 3 pi over 2 has the point 0, -1. X-coordinate of 0 means the graph goes back to 0. The cosine value is 0. And once again, ending where we started, 2 pi has the same point as 0, 1, 0. The x-coordinate is 1, so again, the cosine function ends just where it starts. It goes from 1 to 0 to -1, back to 0, and then back to 1, making one full cosine wave. Or this one really looks like a cup, right? That's how you can tell the difference between cosine and sine. All right, but once again, the outputs 1, 0, -1, 0, and 1 keep repeating. That's because cosine is also a periodic function. It returns the same values over and over at regular intervals. The period tells us how long it takes to complete the cycle. The period of cosine, we can tell, is exactly the same as sine. It took 2 pi radians to graph this whole thing. We went all the way around the unit circle. So the graph of the parent functions for sine and cosine have a period of 2 pi, and that will become really important when you're graphing these. You need to remember the period of sine and cosine being 2 pi, but that's for the parent function. All right, this is all well and good, and then you get to a point in class or in your textbook where they all of a sudden start talking about sinusoidal functions, and you think, what has happened? How much time have I missed? I understood sine and cosine just fine, and now they're throwing this sinusoidal word at us. Well, it's not that bad. Sinusoidal function is just a funny term that is used to describe a special type of periodic function. So not all periodic functions are sinusoidals. Thank goodness, or we'd hear this word all the time. But sinusoidal functions are periodic functions that form symmetrical waves. You'll remember I said that cosine was symmetrical with the y-axis and sine was symmetrical with the origin. That's why those are both sinusoidal functions. They form symmetrical waves. They're periodic functions that form symmetrical waves. So here we have clearly a sinusoidal function. It is periodic, it is a wave, it is symmetrical with the x-axis. This is a cosine function. Here we have a periodic function. It's clearly returning the same values over and over again. It is symmetric, but it does not form symmetrical waves. It is not sinusoidal. Here, we have a wave, but it is not periodic. If you notice, this is not returning the same values over and over. The outputs are getting increasingly larger and increasingly smaller. This looks like an increasing sine wave. This is not periodic, and it is not sinusoidal. So, all sinusoidal functions are periodic, right? Because a sinusoidal function is a special type of periodic function. But not all periodic functions are sinusoidal. Just because you're periodic does not mean you are a sinusoidal function. All right, that's enough of that word. It'll only come up a few more times today, I promise. But when you think sinusoidal, think sine and cosine, because they are symmetrical waves. Speaking of sine and cosine, let's look at the function for sine and cosine. You have this general form, f of x equals a times either sine or cosine of the argument bx plus c plus d. Okay. In this function, a, b, c, and d are all constants, and a and b can't be 0 because then you wouldn't have a sine or cosine function of any type. Let's identify each piece. A is that value being multiplied to either sine or cosine. It is the amplitude. It is actually what's either stretching or shrinking the function. And the amplitude is a distance. It's half the distance between the maximum and the minimum. So think about it from the midpoint or the midline of the function to the highest point. It's a distance. Because amplitude is distance, it will never ever be negative. Hence the absolute value of A. Okay, B. I know your textbook has a weird definition for B. B is just the number of complete cycles that you'll find in 2 pi radians or in 360 degrees. Okay, so B is not the period, but B is used to find the period. You take the normal period, 2 pi, and you divide it by the absolute value of B. And we're going to talk about how easy that is in a little bit. Phase shift. Phase shift is a new term, but it's basically your horizontal transformation, which you are used to. Phase shift, because it's a little bit different, it's not just that value. It's not just the opposite value of C. You have to find the phase shift by taking the opposite value of C and dividing by the absolute value of B. We'll get into that too. D is as easy as it's ever been. It is a vertical shift with the sign. So plus D means up D units, minus D means down D units. Transformations of sine and cosine functions are so similar to all the other transformations we've learned. So you're going to see how similar they are. That constant factor, this thing that we called an amplitude right here, this is what you're used to seeing as a stretch or a shrink. The constant factor, A, is the scaling factor. So when the absolute value of A, well, when A is greater than 1, it's stretched. When it's less than 1, so it's a fraction, like 1/2 sign, it's shrunk, okay? So think of this as stretching or shrinking that sine curve. So when you have the graph y equals a times the sine of x, it will range between negative a and a, not negative 1 and 1 like the parent function. A is going to change your range. Now, talking about the period of a sine or cosine function, we already saw that one complete cycle for the parent function took 2 pi radians. Sine and cosine have a normal period of 2 pi. But B is going to change that because B is going to say, if B is 2, that means you see 2 complete cycles where you used to see 1. If it's 1/2, you will see only half a cycle where you used to see 1. So B, if B is not 1, if you have some coefficient on x or on theta that isn't 1, your period's not going to be 2 pi because B will affect the period. B says how many cycles you see between 0 and 2 pi. Well, normally that's 1. So if it's greater than 1, that means you see more than 1 where you used to see 1, the period's smaller. It's going to take less time if you're going to put 2 complete cycles where 1 used to be. If B is less than 1, the period's larger. Because if you're only going to see a half a graph where you used to see 1, it's going to take longer to make 1. Let's consider this function y equals 3 times the sine of 2x. I don't really want to graph it step by step, but I want to talk about each piece and then look at how it relates to the graph. So the value 3, that's our A value. Our amplitude is the absolute value of 3. So this graph is stretched up to 3 and down to negative 3. The 2 tells us that where there used to be 1 complete sine curve, there will now be 2. Since B is 2, this will make 2 complete circles where there used to just be 1, meaning the period is going to be smaller. In fact, since we're making twice as many circles as the parent or cycles as the parent function, the period will be half as long. The period formula is 2 pi over b. Doing 2 pi over 2, you see the period is pi. It makes sense that to see twice as many sine cycles, you would have a period half as long. Now let's sketch the graph. Again, I'm just going to put it up here. This is the graph of 3 times the sine of 2x. Let's see what we can notice. It still starts at 0. That's not going to change. The period is pi. So you'll notice that 1 complete sine cycle is made between 0 and pi. The amplitude is 3, so it goes up to 3 and down to negative 3. Okay? So when I make my cycle, I'm not going to stop at pi. Right? B says there's 2 between 0 and 2 pi. I'm going to show both of those cycles. So I'm going to draw the one cycle right there, and then the second cycle right there, making sure that when I draw my curves or my waves, I go all the way up to 3 and all the way down to negative 3. Remember, B was greater than 1, therefore my period was less than the normal 2 pi. It was actually half of that. Let's talk about phase shifts. These are really just your horizontal transformations, but these are the part of graphing, or this is the part of graphing that gives people trouble. The constant C in that general formula, A times sine or cosine bx plus C plus D, is what creates the horizontal translation. Okay, so C isn't all by itself the phase shift, but it creates it. So let's remember back to when we were in algebra and we were dealing with quadratic functions. If we had something like f of x equals x minus 4 squared, the part inside the parentheses was our horizontal transformation, and it moved opposite the sign. So this graph moved 4 units to the right. The same type of thing happens with these sine and cosine functions. Horizontal translations with these sine and cosine functions are called phase shifts. And to find them, you do negative c divided by the absolute value of b. Okay? And I know it seems really weird, but really when we graph a function that has a phase shift, think about it. A phase shift is pushing this function horizontally. So it's changing the starting point because it's pushing this graph. So it's going to change the starting point, and then subsequently it's going to change the ending point. All right, so what we're going to do is find the new starting point, find the new ending point, and calculate the distance between the points or the scale of the graph. And that's going to make it much easier to actually plot. Okay, so remember, phase shifts moves those starting and ending points. What was our parent function starting and ending points? We started at 0, we ended at 2 pi, right? We used the unit circle. So those are going to be pushed if there's a phase shift. So when we find the new starting points, we'll do it like this. We will take everything inside the parentheses, right? Everything inside the parentheses is causing our horizontal movement. So we're going to take what's inside the parentheses and set it to 0. Why set it to 0? Because 0 was our original starting point. So we need to set it equal to that to see what's changed about it. To find the new ending point, take what's inside the parentheses and set it equal to 2 pi. Because 2 pi was our old ending point. All right, let's just look at a phase shift. We're going to identify the phase shift in this function f of x equals 2 times the sine of the quantity x minus 2 pi. How do I know there's a phase shift? Because I have a c value, right? I have x plus or minus something in here. So my phase shift formula says take negative c divided by the absolute value of b. C right here, right? This is c, negative pi over 2. B is 1, the coefficient of the variable. So let's put that here. And if I employ the formula, I can probably see the phase shift here. I don't have to do negative c over the absolute value of b, but I'm going to do it. Negative times negative pi over 2 divided by the absolute value of 1. Well, that's just negative 1 times negative pi over 2. I get positive pi over 2. So my phase shift is positive pi over 2, meaning the graph is shifted pi over 2 radians to the right. Remember, transforming parent functions within the parentheses is your horizontal shift, and it's always opposite the sign. I saw a minus sign in my function. I knew I would be moving to the right. Okay. When we graph functions with a phase shift, it is more easily done by saying, what is my new starting point? What is my new ending point? Even before you find this pi over 2 if you want. Let's find our new starting point. Take the inside of the parentheses and set it equal to 0. You're going to set everything inside the parentheses equal to 0. So x minus pi over 2 equals 0. Now we solve for x. And how do we do that? We add pi over 2 to both sides. We get x equals pi over 2. That's our new starting point. That should make sense, right? Because that's pi over 2 radians to the right of 0. 0 was our old starting point. If we moved pi over 2 to the right, we should be at pi over 2. Let's find our new ending point. Take the inside of the parentheses, set it equal to 2 pi. X minus pi over 2 equals 2 pi. Add pi over 2 to both sides. Now we get the ending point at 2 pi plus pi over 2. This involves adding fractions, and adding fractions in the form of radians, our favorite thing to do. So 2 pi, remember, with a denominator of 2 is 4 pi over 2. So our ending point happens at 4 pi over 2 plus pi over 2, or 5 pi over 2. Okay, we are going to take step-by-step graph this function. We now know the starting point, we know the ending point, we know the phase shift. We'll talk about a few other things, but let's get this thing graphed. Graphing sine or cosine functions. These are the steps you take. The first step you're going to take is the easiest. You're going to calculate the amplitude. The amplitude is the absolute value of A. In this case, it is 2. So my graph will go up to 2 and down to negative 2. Step 2, find the period. If you do not have a number multiplied to x, your period has not changed. This says I see one complete cycle in 2 pi radians. So my period is 2 pi over b, 2 pi over 1 is 2 pi. My period is unchanged. Your period will not change if you do not have a number multiplied to x. Step 3, find the phase shift. We just found the phase shift as negative c over the absolute value of b. It was positive pi over 2. There is no vertical transformation. We don't have to worry about that. Step 4. Now, this is the step that's new. You have to calculate the new scale for your graph. Calculating the scale for your graph. Take the period of your function and divide it into 4. You need 4 sections for your graph. Think of the 4 quadrants on the unit circle. That's what you're doing. 2 pi divided by 4. So my scale is pi over 2. That means I'm going to count by pi over 2 along my horizontal axis, or the scale of my graph. All right, lastly, find your starting and ending points. You have a phase shift, so you got to take what's inside the parentheses, set it equal to 0 to find the starting point, equal to pi over 2 pi to find the ending point. We already did that. The starting point is pi over 2. The ending point is 5 pi over 2. All right, let's draw our grid. Okay, notice I put a little sideways T, and I made 1, 2, 3, 4, 5 tick marks. I am going to put my scale on here. My scale starts with my starting point, pi over 2. So I put pi over 2. And then I count by the scale, pi over 2. So I'm going to say pi over 2, following the unit circle. What's the next point pi over 2 away? That's pi. Then 3 pi over 2. Then 2 pi. What's my ending point for this graph? My ending point is 5 pi over 2. That's going to be my last tick mark. All right, what else do I have to change? I have an amplitude. My amplitude is 2, so I have to go ahead and mark those. That's not going to be 1 and negative 1. It's going to be 2 and negative 2. Now I can plot my values. Remember, the sine cycle goes in the same way. 0, 1, 0, negative 1, 0. So we are simply going to plot our points. 0, 1, 0, negative 1, and 0. And we are going to draw a curve through those points. And there we have it. That is our sine graph for the function f of x equals 2 times the sine of the quantity x minus pi over 2. One really important point. You must label the values on this scale. So the scale we found by doing pi or period divided by 4, we have to put these values or you will not get credit for graphing this function. Still have questions? You should be subscribed to our YouTube channel. Send those problems in to me and I will make you a custom video solution. Till next time, Math Hoppers, take it easy.